My bad. Didn't mean to confuse you. Okay. So we are starting in Chapter 2B, more derivatives, further differentiate, or call it. That's what we're doing is more. More starting with something like this. Now, you guys did get from hopefully someone in your group the following grid. Everybody got one, right? Okay. What does this say at the very top? What's this assignment? AP number 1, functions, derivatives, and their graphs. I wonder what's going on. It's like a table you're supposed to fill in with stuff. Oh, it seems like they're numbered. Like maybe somehow they go together. I wonder if we're matching things. Ooh. I want you guys to be pondering during class, if there was to be a partner project, a partner assignment, who would you choose and would they be down with it? In period 6 and or period 1. It could be both. Doesn't have to be this period. Period 1 has been thinking about it. They might have already started asking you guys. You guys get to think about it as well. If there was a partner assignment, who would you reach out to? Who would you choose? Maybe looking around the room being like, I don't know. You have all class to think about it. All right. Here we go. Question. Okay. I'll give you 30 seconds if you actually need to like make contact with someone right now. Ready, set, go. If you want to check, you can check. You also have period 1 as options. You also have period 1 as options. All right, 10 more seconds, and then we need to quiet down on the whole checking with people. Doesn't have to be figured out right this second, but some of you were very excited and wanted to reach out right away. 5, 4, 3, 2, 1. Okay, notes 2.5. Chapter 2A. Chapter 2A had sections 2.1, 2.2, 2.3, and 2.4. Chapter 2B, 2.5, 2.6, 2.7. 3 sections, 1 whole test in about 2 weeks. 3 sections, 1 whole test in about 2 weeks. There's a lot going on. This section, 2.5, I'm starting it and introducing it today. I was going to start off with the partner match project, but I'm going to start off with this section because some of you guys aren't going to retreat. And you would love to get ahead a little bit, or even just stay on top of homework. And so to do that, I want you guys to all get a quick introduction to section 2.5, enough to which you guys could work on it over the weekend, okay? This homework is a little brutal. It's a little bit of a beast. It's not due the day we get back. It's not even due the next day. Oh, I didn't even write it down, sorry. It's not even due the next day after we get back. I think it's probably due the Friday we get back. But it's a bit tricky, so let's get the main idea today. And the main idea is that you're going to be given equations, functions, expressions that do not have, what's weird about this?
There's a y.
There's a y. Wait, there's always been a y. So what's weird?
It's connected to the x.
It's connected to the x. It's not, what were you trying to say, Kyrie? I think I agree. It's not what? It's not by itself. It's not isolated. It's not solved for. Now, chapter 2a. What would we have done if they said find the derivative and y is not by itself?
Subtract 3x.
Yeah, get y by itself. Okay, so if we had been given this problem earlier, maybe just a few of you would have figured out, well, why don't we just get y by itself? It's going to look like what we want it to look like. What do you guys think? 10 minus 3x all over x look good?
Yeah, you could probably.
Right? Take away 3x, divide the x. Is that true? Yeah. Okay. Why do you like it better now? Oh, because this is derivative, and we can do derivative. Okay, got it. So do derivative. We end up with bottom, d top, minus all over. Oh, we just gave Colby a hint. Just kidding. He's taking the test in the back. Okay, shh. Pause. Was there any other way to go about this problem rather than just diving into the quotient rule? What were you thinking, Lainey?
You could divide it by x.
You could have rewritten?
Yeah, rewritten. It's kind of x, then
I like taking that derivative. But was quotient rule illegal? Oh. Numerator, denominator, top, bottom, it's okay. But was it as easy as? Well, for some of you, this jump is a lot harder than just going there. So either one's right, either one's correct. What do I mean? Either one's right, either one's correct. Guys, what do we call derivatives again? What should be over here? Okay. I meant as far as notation. Sorry, I wasn't very clear. We would end up with what? Negative 3x minus 10 plus 3x. Don't kill a seal. Final answer for the derivative for dy dx. Like we're used to, we got y by itself, took the derivative. Negative 10 over x squared. Do you guys agree? Yeah. What if we had rewritten first and then taken the derivative? What would my dy dx have equaled? Which is, oh, hey, look. Okay, so even though there were two different ways to go, both of them started with getting y by itself and taking the derivative. But has anybody ever wondered why the derivative of y is dy dx? Why is the derivative of y dx? Did anybody, when you were writing this down and starting to think about finding the derivative, did anybody think of any other way of going besides getting y by itself? Huh? Limits are going to be messy too because we'll still have to get y by itself to plug into f of x plus h. So limits, you'd have to get y by itself also. So it'd be the same beginning step. Anybody think of anything else besides going straight to the limit definition or besides quotient rule or rewriting? Oh, no one? Patricia's the only one to think of it today, huh? What? Oh, deriving both sides? What would that look like? What would we have started with? If we took the derivative of both sides, what would we have had to do first? How did we derive this, though? Oh, product rule. Maybe a chain rule, too? Do you guys realize that in between this and this, there actually is an in-between step, how to go from here to here? Have you ever realized that? Technically, what you're doing to get dy dx is you're saying, hey, I need to take the derivative of that y guy. And the derivative of that y guy says bring down a 1, make the power 1 less, and then multiply by the inside prime. Y prime. Technically, every time you went from here to here, you were actually taking the derivative of the y like you would in x, but you couldn't just put 1, y to the 0, 1. You also had to put a dy dx. I wonder what happens then, if that's when we take the derivative of y, I wonder what happens when we take the derivative of x. Why is it just 1? If the derivative of y is that complicated, why is the derivative of x not complicated? To take the derivative of x, don't we do the same thing of bringing down the 1, subtracting 1 from the power, x to the 0, which is why it goes away, times x prime? What's x prime? Dx dx? But what happens to dx dx? Oh, the derivative of x is just 1. The derivative of y is dy dx. They work the exact same way. We just didn't talk about implicit differentiation earlier to say, hey, you know when you're taking the derivative every time with quotient rule or even with power rule, when y is by itself, you're actually every time you're taking the derivative of the y. So if you can take the derivative of the y when it's by itself, can't we take the derivative of the y when it's mixed up? Here's what our dilemma is that we're going to have to face in section 2.5, implicit differentiation. What if the mixed up functions are harder than this guy? This guy, you could have just gotten y by itself and gotten to the final answer and been correct, been done. But there is another way that we could have gone. I'm not going to go that way quite yet, taking the derivative of both sides, starting off with product rule. But first, before I even show you the alternate way of going, let me show you the dilemma and why we need to go further and not just stick with, just get y by itself every time. Because what if you were given that? Get y by itself. Yeah. I squared. Yeah. Get y by itself. Unfoiling is also known as factoring. Good. How? How do we factor that trinomial? Okay, so we put 5x up here, and then we put the negative 3x. Only one can have an x and one can't have an x? That's not possible, is it? Because an x times 1 is but an x. Because I can't combine those to be him. So even if I did get a number to make 1 work, well, it's not, I can't because it doesn't have. Okay, modified x method is not a good idea. But factoring is a great idea. How many of you guys think it's impossible to get y by itself? Oh, wow, you all have a lot more faith than I thought you did. Okay, someone give me an idea then. If you think you can get y by itself, give me an idea. How? Sure, subtract 5x. Then what? Pull out a y. Problem is you now have a y still in 2 spots. What else could we do? Divide? By what? 3x? We can move that over. We could divide by 3x. Yay! But then have to divide by 3x. Oh, he's stuck again. No one's going to think of square rooting stuff? Why don't we move that to the other side? Let's square root. How do you square root that? You don't. Oh, then get that alone and square root him. Great, but now he's stuck under a square root. Well, that didn't work. Huh? Okay, so if we move the 10 over and we group, we could pull out a 5. We'd have an x plus 2. We could pull out a y and we'd have a y minus. It wouldn't match. Good idea. Wouldn't match. Huh? But we're saying to get y by itself. So hang in there, Kevin. I know. We're close to that. He's just wanting to go. He just wants to take a derivative right now. But no. We're trying to get y by itself. We could factor out an x, but then we would have the y squared and a y plus 1, and we'd have no way to get the y's in one spot. But we could then divide the x, but then he's going to be stuck here with an x.
So how come we can't do the square root? Use dimensional.
Because if you try to square root that, you can't pull anything out. It's illegal. If you just try to square root him, everybody else has to be on the other side under their own square root, and now they're trapped in 2 separate spots. Yeah. Who thinks it's impossible to get y by itself? I've only convinced 2 of you. Okay. What else could we try?
Oh, wait, is it impossible? Okay, I read mine.
Well, tell me how. If you think it's possible, tell me how. Kyrie.
I don't think I can. I just don't know.
Plus what?
9 over 5 square root.
He's got it.
Oh, I couldn't hear it.
It's interesting. A lot of you guys think it's possible just based on reading me, even though you have no clue what to do except for Kyrie.
Yeah,
Unless someone else thought of this.
what I can.
He's telling me to add 9/4 x squared on both sides.
What?
Why?
Correct. Oh, complete the square.
Hannah, it wasn't so random yesterday.
No. It's fine.
You have to take the middle term and cut it in half, square it, right? And what you add to one side, you have to do to the other. Abby's not very happy. And then we need to factor it. And then we would get y minus 3/2 x quantities squared equals negative 5x plus 10 plus 9x squared over.
Worse.
Y's alone. Or he's almost alone. He's in one spot. Now we can unsquare it, aka square root it. Square root of a squared is an absolute value, and so to get rid of the absolute value, you do need plus or minus. I'm going to write this a little bit nicer. 9x squared all over 4 minus 5. And then, whoo, look at that. Can y be gotten by itself? Yes. But should it? Can y be gotten by itself? Yeah, but should it?
No.
If we're supposed to be finding the derivative, oh, we could. Derivative of y is dy dx. Derivative of 3/2 x is 3/2 plus or minus. Okay, it's a chain rule. Something 1/2. Let's go. You actually can. You actually can get y by itself and then take the derivative. But should you? Which one looks easier? Taking the derivative here? Or just taking the derivative way back there? So let's learn how to do the way back there. But let's not start with this problem. We had an easier problem just a second ago with the other guy. But before we start with the other guy, talk just really quickly about another way of looking at it. Up until this point, and I've kind of already introduced to you guys what I'm about to write. Up until this point, you've been saying y equals, sweet, x, let's take the derivative. But what you weren't realizing is every time you said, sweet, dy dx equals, you were taking a derivative. You've always derived both sides. You just might not have ever realized it. So I'm going to write over here real quick. To take d dx of x to the 1. Some of you might have written this before, some of you might not. To take the derivative of x to the 1, you do bring down the 1, subtract 1 from the power, and multiply by dx dx. I just haven't really shown this to you before. Which does end up just everything simplifying to be 1. We know that. But here's why. And when you take d dx of y, which you guys in your head just said, take the derivative of this guy. Sweet, it's dy dx. But why? Because you bring down the 1, you subtract 1, so the y just goes away, but you need to do u prime, y prime, and y prime is dy dx. So that's all 1, but 1 times dy dx is dy dx because of the chain rule. That's why I couldn't have shown it to you earlier. It's because of the chain rule. So why dy dx? Because dy dx is the derivative of y. So what do we do if we have something like, keep me honest, the first example, which was xy plus 3x equals 10. Okay. Let's say we have that first example. And let's say we don't want to get y by itself. Or we know we're in this section where everything is mixed up and you're just supposed to go for it. Could we take the derivative of both sides like you've technically always done, even though it looks a little differently now? Yes. In algebra, didn't you learn what you do to one side, you have to do to the other? So all this time when you've been saying the derivative of the right side, technically you weren't doing the derivative of the left side. You weren't saying y equals the derivative. You were saying y prime equals, or dy dx equals, or f prime of x equals. You were taking the derivative of the left and the right. So let's just do it here. And when we take the derivative of the left and the right, well, let's start with the right, because he looks easier. What's the derivative of 10?
0.
Believe it or not, it's the easiest piece, and yet it's the one most commonly mistaken. Because people get so tired over here, they forget to do that. The derivative of 10 is 0, not 10. Okay? Derivative of 10 is 0. We'll take this guy's derivative too, though, right? I'm mixing up all my markers. Why am I doing box triangle? Oh, this is going to be hard. The y is in there with the x. I don't know what to... Pause. Product rule says what? Second. D first. No big deal. Plus first. Ooh. What's the derivative of y? Yeah, it's just dy dx. You could actually also put, if you like it a little bit better, you could put y prime. The problem is if you start having y's and y primes, if your writing is messy, you're going to start mixing them up and not keeping track of who's who. So I write dy dx to make sure in my brain I know they're two very different things. Hold on, that's just product rule. Second d first plus first d second. We still need the plus who?
3.
Careful. Derivative of 3x, which is 3. Technically dx dx, it always goes away. But I want dy dx, don't I? But can't we just get him alone? Oh, okay, so dy dx is equal to, we need to subtract the y. 0 minus y is negative y. When you divide by the 3 and the x, dun 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 dun, it looks differently than the one we found. Yeah, the tone wasn't quite right. But, question, are they the same thing? Can you look at the very first problem that we did? Are they the same thing? The answer we got was negative 10 over x squared. How can I compare? I got this one with y's and x's. Is it the same? Maybe. Is it different? Maybe. How could I tell for sure? Go back and say, well, wait a minute, who is y? Oh. See, if you don't get y by itself at the beginning, and you need to get your answer with only x's, because the multiple choice answers only have x's and not y's, you still have to go back to the beginning and get y by itself. Then once you get y by itself, which we already did, so I just wrote it down, you could just plug it in, and make sure it matches. So, negative 10 minus 3x all over x. Wait a minute, how do we deal with a complex fraction? No stress, right? Nice thing is, this whole thing is over an x, so I can... Oh, thank you, Lorenzo. I was going too fast and thought it was a times. So our derivative's a little bit off. Lorenzo just helped us out. We have to subtract the 3 and subtract the y. So it'd be negative 3 minus y. I thought that was too easy. So when we go to plug in, we'll say, still plugging in, still getting y by itself. Who else saw that and didn't stop me sooner? Negative 3 minus, okay, do we still have a complex fraction though? Yes. Do we still need to multiply top and bottom by x? Yes. But is it as easy as far as just canceling him? No, because he has to go to this guy, which will be negative 3x. And then he has to go to this guy, where he's going to reduce and just be negative 10 plus 3x. Why is it plus 3x? The x is canceled. Oh, a negative times a negative, right? Okay, so then those cancel. Oh, hey, it is the same thing. Now pause. Did you guys check, you hear what I said about if? We only have to go back looking for y if all of the answers are in terms of what? Okay, so if when you're doing homework, this is a very important strategy. Isn't homework take a derivative, you're going to say, yay, I think I got it. And where are you going to go to look? The back. And you're going to ask yourselves, did the back leave it with x's and y's, or is it only x's? If they left it in x's and y's, should you? Yeah. Because all the answer choices would have had x's and y's. You would have known it in a multiple choice question. Oh, I can leave the y's. Sweet. It's only x's. What does your brain need to say? Let's go figure out how to get y by itself and plug it in, Or let's go look at the original expression and say, can I plug in 10 for something that's magically, oh no, he's not there. This exact statement isn't anywhere. If this exact statement was in the answer, I could just put in 10. That's really tricky sometimes. But if theirs looks differently than yours, ask yourself, number 1, do I need to go get y by itself and plug in? Number 2, is there something that the original expression was able to substitute in for? Number 3, oh, did I make a mistake? But here's the new way. The other way of looking at it says derive as it is. The new way says just take it as it is. Don't try to change it and make it what you want it to be. Just go. Take the derivative as it is. You don't need to get y by itself. So even though you're used to y being by itself, it doesn't have to be every time. You just need to remember, well, explicit functions, that's not bad. That's what we've been seeing all this time. Uh-oh, where did my thingy go? Where'd you go? He disappeared. Explicit functions, that's what we've been seeing this whole time. I'll just leave it. Sorry, forms of functions. We've been seeing y is by itself with the function on the other side. Explicit function, we've been going down and saying, oh, dy dx is equal to f prime of x. But technically, what you were doing was taking the derivative of the left and taking the derivative of the right. Just the left was easy, because if it's just a y, the answer is just 1 dy dx. We would spend all of our time and all of our work on the right-hand side. What's different with implicit? Well, now, sadly, I can't even show you like both sides, because who knows what's going to be there. So I'm just going to say instead, now we have a function in terms of x's and y's. And to be honest, actually, we're going to have equations with x's and y's. Some of them are functions and some of them are not. If y can be squared all of a sudden, it might be something like a circle or a sideways parabola that's not a function, but it's still something that we can take a derivative of. We're just going to have to take a derivative of both sides. So I can't show you exactly what's on the left or what's on the right. I can say it'll probably be in terms of x's and y's, but we're going to take the derivative of both sides just like we did over here. But when you get your derivative, he's going to be implicit also in terms of x's and y's. And you're only going to be able to get him in terms of x by substituting. You're going to get a derivative in terms of x's and y's. And that's not bad. Some multiple choice questions. Some answers in the back of the book, leave the x's and y's because it's too crazy, too ridiculous to go back and find y. Maybe it's impossible or maybe it's just not. Oh, what's the word that they use? Or why did it just fly out of my brain? It's a Friday. We'll blame that. Reasonable. It's not reasonable to get y by itself. But if you do want just with x's, you are going to have to come back and say, is there a way to get y by itself? If there is a way to get y by itself, we could go on and plug in. Or is there a way to take the original clue and somehow plug that in? Okay, explicit, y by itself, derivative of both sides, but this one will always be dy dx. Implicit, who knows what you got on both sides? X's and y's are all mixed up, and your derivative will be all mixed up too. So let's do an example. Oh, I wanted to show you the steps. Lo siento. Let me give you a second to get the steps set up. I'm actually going to fill in the steps as we solve the harder problem we started with. So let me give you a second. We are going to go back to that harder problem that we saw a second ago, where there's a y squared and there's an x times a y. We're going to go back to that. But first, let me give you a second to set up what's going on. You only need to skip me really just this line. Really just this line. That's all. This is not a forever card. You're not going to have to memorize it. It's more of just a technique, a strategy, an approach to a problem. We don't normally memorize approaches to problems. It's kind of like we just try to train your brain to get going in that direction when you see problems of this type. It's not really a good memorizing thing. But implicit differentiation, x's and y's are all mixed up. We have to think a little bit differently or just train our brains to think a little bit more properly as far as what we're doing. When we find a derivative, we do take the derivative of both sides. Whatever we've been given, what we do to one side, we do to the other. With the quick, important clue that the derivative of y, aka y prime, is dy dx. And then you guys are writing down collect dy dx terms, collect all terms with dy dx on one side. I say on the left side because we're trying to get dy dx alone on the left. Move all other terms, adding and subtracting, eventually multiplying, dividing to the other side. I'm talking about terms. I'm talking about things being added and subtracted. So I should say move all terms without dy dx with addition or subtraction to the other side. Just a quick hint, quick clue for those that wouldn't see it naturally. If you only have stuff with dy dx on the left, you can factor out the dy dx and then solve for him. So the final goal is to get the dy dx alone with, I don't know, some sort of derivative, probably with x's and y's. The final goal is to get dy dx alone. So as soon as you guys have those steps, we're going to come peek at this guy. Find dy dx 4. Okay, this is the guy we saw earlier. This is the guy where CalcAB figured out if you complete the square, you can get y by itself. But then we were like, ugh, I don't think we want to do that. So don't. Take d dx instead and say that you'll find him another way. Okay. What's the derivative of 10?
0.
Don't forget that. Derivative of any constant, always 0. What's the derivative of y squared? 2y. Don't forget your u prime. Who's inside the y squared? Y is. And who's y's derivative? dy dx. Derivative of the outside is 2y. Derivative of the inside is not dx dx anymore. It's dy dx. Minus. What's the only legal way of going about the derivative of of 3xy? Yep, it's a product. So second, d first plus first. What's the derivative of y? Oh, that's right, we know that. Now what's the derivative of 5x? How are we doing? Does it make sense? Every time you take the derivative of y, or of a y term, you just have to remember your y prime at the end. Just the derivative of y, well, it's dy dx, no big deal. So if I rewrite this, you guys see how some terms that are being added and subtracted have a dy dx and some terms don't? Who doesn't have a dy dx attached to the term? And what else? So move them. How? Well, he needs to be added and he needs to be subtracted, true? So adding the 3y, subtracting the 5, and they're gone. Now what does everyone who's left on the left have? So what can I do if they all have dy dx? Yeah. And when you factor it out, it's in one place all of a sudden. And now that it's in one place, how do I get dy dx alone, my final objective? Divide. Bingo. Kiddos, on this problem, on the AP, they would not have expected you to complete the square to get y by itself and then take a derivative. That is algebraically way more rigorous than they would expect you, or than what they would expect you to need to do for any derivative problem. They would expect you to do it implicitly, and you would have known because you could have looked at the multiple choice answers and been like, ha ha, the derivative has y in it, sweet. Take the derivative of both sides, let's go. And ironically, it doesn't just have y's. Oh, who did I forget to write? Thank you, thank you, thank you. It's like, that's weird, why are there no x's? There's one. What was that? What is this? Something that we call implicit differentiation, but we're going to do more next week. For right now, I want you guys to get out this little chart. You've been pondering, you've been thinking, if I was to partner up with someone, who could I ask? Maybe even with a few backup options, because you're like, I'm not sure they'll say yes. That's okay. Period 1, period 6, there's multiple people. Ooh, what's this?
I actually know what that is.
It's called an overhead projector.
Wow.
With overhead transparencies. Whoa. It's like asking a kindergartner like what a turn dial telephone is. You guys ever watch those? Like asking kids what like that tape play? Well, you guys probably don't even know. Anyway. I had a Walkman. I had a CD player. I had a 5.5-inch floppy disk. Anyway, okay, we're done. Here's the dealio. What you have before you is a grand old thing that we call a matching assignment. Shh. It's a card matching game. It's a card matching assignment. All of these need to get put into groups of 4. Groups of 4? Look at your table. All of these need to get grouped into groups of 4. Let me show you what the different categories are. Read the first column. What's the first column say? Function graph. Hey, look. Here's a function graph. Sketch of this function graph.
Yes.
You're not going to have to fill out what the card says on every